For as long as anyone watching this has been alive, the textbooks agreed on one thing about Betelgeuse. The most famous dying star in the sky had roughly 100,000 years left. Comfortable, distant, somebody else's problem. That number just quietly fell apart. Between 2024 and 2026, astronomers discovered Betelgeuse was never alone. A second star is hidden inside its atmosphere, and this past January, a Hubble result caught its wake. The light you see tonight left that star 600 years ago. This is the story of what it's doing right now, where none of us can see. For most of the last century, if you asked an astronomer about Betelgeuse, you got a calm, confident answer. It is a red supergiant, it is enormous, it is aging, and it is absolutely destined to explode. But not soon. The number people quoted was roughly 100,000 years. 100,000 years. That is not a threat. That is a comfort. It is a stretch of time so far beyond a human life that it rounds down to never. Your descendants, 500 generations from now, would be the ones to deal with it, if anyone ever did. So we looked up at the orange star on the shoulder of Orion, we admired it, and we went back to our lives. That answer was everywhere. In the textbooks, in the documentaries, in the confident voice of every science explainer who ever pointed a camera at Orion. It carried the full weight of consensus, and consensus is a kind of gravity. Once everyone agrees on a number, you stop checking it. Here is what almost no one outside professional astronomy understood. That number was never a measurement. You cannot point a telescope at a star and read its remaining lifespan off a dial. What astronomers did was build a model. They took what they knew about Betelgeuse, its mass, its brightness, its temperature, and they fed it into equations that describe how a star burns through its fuel and dies. The 100,000-year figure was the answer that model produced, and the model rested on a single assumption so basic that almost nobody thought to question it. The assumption was that Betelgeuse was alone. It was not alone. In the summer of 2025, a team led by Steve Howell at NASA's Ames Research Center pointed one of the sharpest instruments in astronomy at Betelgeuse. It was a speckle imager called Alapeak, mounted on the 8-meter Gemini North Telescope in Hawaii. And after decades of everyone assuming they were looking at one star, they resolved two. There is a companion orbiting Betelgeuse. It is faint, roughly 100 times dimmer than the giant it circles, and it had been lost for all of history inside the glare. Astronomers had nicknamed it before they could even see it. They called it Beetle Buddy. When the detection came, it earned a real name, Siwarha. Follow-up observations with the Chandra X-ray telescope ruled out the frightening possibilities. It is not a burnt-out white dwarf. It is not a neutron star. The best estimates put it somewhere between roughly 1/2 and 1.5 times the mass of our own Sun. Most likely a young star that never quite finished forming, orbiting a giant that is already dying. Now hold on to the next part, because this is where it stops being a footnote and starts being unsettling. Siwarha does not orbit Betelgeuse from a safe distance. Its path carries it to only about 2.5 times the radius of the star. And Betelgeuse is not a small object, with a clean edge. It is a red supergiant so vast that if you dropped it where our Sun sits, its surface would swallow the orbit of Jupiter. Picture that for a moment. A single star wide enough to contain the Sun, and Mercury, and Venus, and Earth, and Mars, and most of the distance out to Jupiter, all inside its surface. That is the thing Siwarha is orbiting, and it is not circling from a safe height above. A companion orbiting that close is not out in space somewhere. It is moving through the outer atmosphere of the giant itself. Not around it. Inside it. Every orbit, Siwarha plows through the star's outer layers like a swimmer through water, and it leaves a wake. The strange thing is that the evidence had been sitting in our data for decades. We just kept explaining it away. Betelgeuse's brightness has always wobbled. There is a main rhythm about 400 days long, where the whole star swells and shrinks, the giant breathing in and out. That part we understood, but layered on top of it was a second, slower cycle, close to 5.8 years, that nobody could fully explain. Papers called it the long secondary period. Some treated it as a curiosity. Some treated it as noise to be filtered out. Nobody called it what it now appears to be, an orbit. In 2024, Jared Goldberg and his colleagues ran the numbers and argued that slow cycle was the signature of a hidden companion. In 2025, Morgan McLeod and his team at the Center for Astrophysics sharpened it, pinning the orbital period to roughly 2,100 days. Think about what that means. The clue had been hiding in a century of brightness measurements. Generation after generation of astronomers watched Betelgeuse pulse on a 5.8-year rhythm and quietly filed it under things we do not understand yet. The second star had been signing its name across our data the entire time. We just kept reading the signature as an accident. And then, this past January, we saw the wake itself. In January of 2026, a team led by Andrea Dupree at the Center for Astrophysics published a result built on 8 years of patience. Hubble had been watching Betelgeuse in ultraviolet light, not to hunt for a companion, but to study the star's hot outer atmosphere, the layer astronomers call the chromosphere. Ultraviolet is where that layer glows, and when the team took 29 of those Hubble observations and folded them against the orbit McLeod had calculated, something locked into place. The fingerprints of gas moving through the chromosphere, the signatures of iron, of magnesium, of manganese, were not varying at random. They rose and fell in step with the companion's orbit for 8 straight years. Every time Siwarha came around, the gas ahead of it piled up, and the gas behind it was dragged outward into a trail. This is what scientists mean when they say a signal is phase-locked. The disturbance was not random, and it was not some internal mood of the star. It was tied to something moving on a schedule, something with a period, and the period matched the orbit not once but across 8 years of watching. Dupree's team used a very specific word for what they were seeing: a wake, the expanding wake of the companion star. Now they were careful, the way good scientists are careful. The companion itself is still described as a probable detection, not a certainty, and this ultraviolet signal is supporting evidence, not a final verdict. But the picture it paints is hard to unsee. Siwarha is not a distant, passive neighbour. It is inside Betelgeuse's atmosphere, stirring it, dragging at it, every single orbit. And that is the quiet fact that broke the clock. Here is why one hidden companion undoes one comfortable number. The clock on a dying star is its mass. A red supergiant is constantly shedding material, bleeding gas off into space through its stellar wind. How fast it loses that mass is one of the most important numbers in deciding when it dies. Lose mass slowly, and the core builds up pressure and heat on one schedule. Lose it faster or in violent, uneven bursts, and that schedule tightens. Mass loss is not a footnote in these models. It is the pace of the entire story. The models that gave us 100,000 years assumed that mass loss was smooth, gentle, and even all around the star. The behavior of a single, undisturbed body. But Betelgeuse is not undisturbed. There is a second star moving through its atmosphere every 5.8 years, compressing gas, dragging it outward, carving a wake. That is not gentle. That is not even. And it means the one number the model most needed to get right, how fast Betelgeuse is losing itself, may not be the number we assumed. I want to be careful here, because this is the point where it would be easy to lie to you. No astronomer is standing up to say Betelgeuse will explode tonight, or this year, or even this century. The mainstream estimate is still measured in many thousands of years at the very least. What changed is not the countdown. What changed is our confidence in it. We had been solving the right equations for the wrong star, a lonely one that never actually existed. The comfortable precision is gone. And once you know the star has been quietly wrestling with a companion this entire time, you start to look back at the strange things it has done and wonder. Like the time 6 years ago when it nearly went dark. In late 2019, Betelgeuse began to fade, not in a flash, slowly over weeks, the way a fire burns down rather than blows out. By February of 2020, it had dropped to the faintest anyone had ever measured in the age of telescopes. Orion looked wrong. People stepped outside, found the shoulder of the hunter, and felt that something was off. The internet did what the internet does. The word supernova started trending. Was this it? It was not. By spring, Betelgeuse had climbed back to its normal brightness. And when astronomers reconstructed what had happened, using the sphere instrument on the Very Large Telescope in Chile, they found something stranger than an explosion. Part of it was dust. Betelgeuse had thrown off a cloud of gas that cooled and condensed into a veil of dust, and that veil scattered the star's light before it reached us. But dust alone could not explain it. The surface of the star had also genuinely cooled, by a couple hundred degrees, across one enormous patch. The images showed it plainly. The whole southern half of the star's face had gone dark, as if something had drawn a shadow across it. What we were almost certainly seeing was a single convective cell, a rising blister of gas the size of our inner solar system, cooling at the surface and seeding its own dust. That is the accepted story now. Cooling first, then dust. And here is the honest, unresolved question that the companion suddenly forces us to ask. Was the timing of that eruption pure chance? Or did Siwarha sweeping through help tear that material loose? Nobody knows for sure. The timing is suggestive, not proven. But the fact that the question is now on the table at all tells you how much has changed. Now step back and remember the strangest fact of all. Everything we have just described we are seeing late. Betelgeuse is somewhere between 500 and 700 light-years away. The distance is genuinely hard to pin down, and the reason is almost poetic. The star is so large and so violently boiling that its own churning surface shifts around and blurs the very measurement we would use to find its distance, but call it, roughly, 600 light-years. 600 light-years means the light entering your eye tonight left Betelgeuse about 600 years ago, around the year 1400, before Gutenberg built his printing press, before Columbus crossed the Atlantic, before Leonardo da Vinci was born. The photons landing on your eye right now began their journey while the 100 Years' War was still being fought. You are not watching a live star. You are watching a 600-year-old recording. Sit with what that means. Everything astronomers say in the present tense about Betelgeuse, that it is losing mass, that the companion is stirring its atmosphere, that the wake is forming, is really a statement about how things stood 6 centuries ago. The star's actual present is, in the most literal physical sense, invisible to us. The news of what it is doing tonight has not arrived. It is still crossing the 600 years of empty space between us, which raises a question that tends to make people go very quiet. What if it has already exploded? What if, 3 centuries ago in Betelgeuse's own time, the core finally gave out, and the light of that death is crossing toward us right now, still on its way, still years or centuries from arriving? There is no evidence that it has, but there is no way to rule it out either, and there is exactly one kind of signal that could tell us before the light ever arrives. When a star like Betelgeuse finally dies, the explosion does not begin with light. It begins with neutrinos. At the end, the core runs out of fuel and collapses in less than a second, crushing protons and electrons together into neutrons. That collapse releases a staggering amount of energy, more than our Sun will radiate across its entire 10 billion-year lifetime, all in an instant. And about 99% of it leaves the star not as light, not as heat, but as a flood of neutrinos. Neutrinos are ghost particles. They barely interact with anything at all. A single neutrino could pass through a light-year of solid lead and most likely come out the other side untouched. They are passing through the planet beneath you and through your body by the trillions right now, as if you were not there. And that is exactly why they matter here. When Betelgeuse's core collapses, the neutrinos stream straight out and race toward us at almost the speed of light. But the visible flash has to fight its way out through the entire body of the star first, and that takes hours. So the neutrinos arrive first, hours before the light, and we are ready for them. There is a global network called the Supernova Early Warning System. It links detectors like Super Kamiokande in Japan, a tank of 50,000 tons of ultra-pure water buried under a mountain, and IceCube, a full cubic kilometre of Antarctic ice wired with sensors. When a star died in a nearby galaxy in 1987, more than 150,000 light-years away, those early detectors caught about 24 neutrinos, and those 24 particles launched an entire field of science. Betelgeuse is hundreds of times closer. If it collapses, those detectors will not catch 24 neutrinos. They will catch thousands in a matter of seconds. The alert would fire automatically. And for the first time in human history, we would know a star had died before we could see it. Picture the moment the alert fires. It is an ordinary night. Orion is exactly where Orion always is. And then, under a mountain in Japan and under the ice at the South Pole, thousands of neutrinos arrive from the direction of the hunter's shoulder. The detectors agree within milliseconds. The system pushes its alert out to every major observatory on Earth. Every telescope that can turn toward Betelgeuse turns. And then the light arrives. Betelgeuse brightens. Not gradually. It climbs hour by hour until it is the brightest star the sky has ever shown a living human being. At its peak, it would shine bright enough to see in broad daylight, a single point of light casting faint shadows at night, perhaps a quarter as bright as the full moon. And it would hold near that peak for months before slowly fading. The colour would not even hold still. In the first hours, the fireball would burn hot and white blue, then cool over the following weeks through white into yellow, into a deep ember red, running through a lifetime of a star's colours in a single season. For those months, Orion would carry a second sun in its shoulder. And you should hear this clearly, because it will need to be repeated many times when it happens. It is completely safe. A supernova is only dangerous within roughly 50 light-years, and Betelgeuse is more than 10 times farther away than that. The neutrinos passing through your body, on the night the alert fires, will not harm a single cell. The danger from a Betelgeuse supernova is honestly the danger of a very bright sunrise, which is to say, none. What it would be instead is the most watched event in the history of the sky. And then, over the months and years that follow, the light fades. The explosion leaves behind a spinning core, a neutron star barely 20 kilometers across, yet heavier than our entire sun, all that remains of a giant. Around it, the shattered outer layers of the star race outward, and over the coming centuries, they will bloom into a vast glowing cloud, a new nebula in Orion that our descendants will study for thousands of years. But the part that stays with us is quieter and simpler. Orion's shoulder goes dark, the orange star that has anchored that constellation for the whole of recorded human history, the one that appears in ancient star catalogues, in the sky maps of cultures on every continent, in every photograph of the winter sky anyone has ever taken, will simply not be there. Children born afterward will learn a different Orion. They will look at our old photographs the way we look at pictures of a skyline missing a building that was always supposed to be there. That is the ending we are promised, eventually. But here is where we actually stand tonight. We told ourselves a comfortable story about a lonely star with 100,000 years to spare. The star was never lonely. The companion is real. The wake is real. And somewhere in the 600 years of darkness between us and Betelgeuse, the truth of what it is doing right now is already on its way, carried by light we cannot rush, and maybe one day by a flood of ghost particles that arrive first. We cannot know what is happening up there tonight. We can only keep watching the old light and wait. Thanks for watching, and I'll see you in the next one.